In this video, we're going to decide whether or not each of these geometric series converges or diverges. And if it does converge, that means that as n gets infinitely bigger, that the sum is going to slow down and approach a specific number. So if it does converge, we're going to find what number that is. If it diverges, it means it doesn't approach a specific number, so we don't need to worry about it. To figure this out, we're going to use the geometric sum formula. And so first we're going to have to identify r. And so I'm going to take 243 divided by 270 to get that common ratio. And I'm just going to verify that it's correct by taking 270 divided by 300. And so we can see that our geometric common ratio there is going to be 0.9. So my partial sum would be found by taking my first term times 1 minus 0.9 to the nth power over 1 minus 0.9. So from here, this means that our numbers, our terms, are getting smaller and smaller and smaller because each time we're taking 90% of the previous. So that means the numbers that we're adding are getting smaller, so my sum is going to slow down. So this part of our formula, 0.9 to the nth, if I take 90% of 90% of 90% of something, eventually it's going to dwindle down to nothing. So take this square, for instance. If I take 90% of it, that'd be roughly that guy. Then I took 90% of what's remaining, that'd be roughly this much. 90% of what's remaining there be here, and continue this on and on and on, and pretty much I'm going to be left with next to nothing as I continued this forever and ever and ever. And so we can say that as n approaches infinity, that this 0.9 to the n is pretty much 0. And so if it's pretty much 0, I'm going to replace it with an actual 0. And so I will end up with 1 over 0.1 times 300, which will give me 3,000. Now, we could verify this by finding a large sum, so we could do this in our calculator. We could start at, the first term, so x equal to 1, and we could go through, let's say, the 100th partial sum. So we could add the first 100 numbers together. We're starting at 300. This is geometric, so we're multiplying. My common ratio was 0.9 to the power of x minus 1. And it will take your calculator a minute because it has to find all of those 100 terms first, but we do get a number close to 3. We continue to increase this sum, and it's just going to get closer and closer to 3,000. So this does converge, and it converges to 3,000. So in our next one, same idea. We have another geometric series, and so we want to first find this r. So I'm going to take 62.5 divided by 50. Take 50 divided by 40, and so I get 1.25 is my r value. So to find my partial sum, I'll take my first term times 1 minus 1.25 to the nth. Oops, I'm going to take off the parenthesis. All divided by 1 minus 1.25. Now with this one, our terms are growing each time. And so 1.25, if I'm adding 25% to the previous one, so we're taking 125% of each of the previous, my sum is going to continue to grow. So we would expect this, our sum, to also continue to grow. And we could look at a graph just to verify this. So I'm going to go ahead and type in this formula into y1 so we can actually see what's happening to the sum. So I'm going to insert in a fraction just to make sure that we get everything typed in correctly. Again, we're using x's instead of n's. And then 1 minus 1.25 is negative 0.25. So I'm going to go ahead and adjust my window a little bit, and I'm going to look at from the first partial sum to the 100th. I'm going to count by 10, and then I expect the sum to get pretty large, so I'm going to go ahead and start at 0, and we'll go up to 1,000, and we'll count by 50. And let's see what this graph looks like. So you can see that my sum isn't approaching a specific number, it's increasing exponentially. And so this one is not going to converge because as n goes off to infinity here, so does 1.25 to the nth. And so we would say that this diverges. Now, while we're looking at graphs, let's go ahead and look at the difference in the graph of the first one. So we were starting at 300, and our common ratio was 0.9. So we'll go ahead and delete that guy. So we have 0.9, same thing in the denominator. We ended up having positive 0.1. So we'll go ahead and look at this graph with the same scale, which it looks like it's doing the same thing, looks like it's increasing exponentially. Well, that's because it was converging to 3,000. So I'm going to go ahead and adjust this, and I'm going to go up to 3,500. And so you can see that it does taper off, and as we continue to add more terms, those terms are so small that our sum does converge to a specific number. So since this number was smaller than 1, our terms were decreasing, which made us converge. Here, our ratio is larger than 1, which means that my terms are growing, which means that my sum is also growing, which makes us diverge. So let's look at this last one. We haven't seen a ton like this, but you can see that our terms are going from positive to negative, well, positive to negative. So that tells me that my ratio is negative. So I could take 3610 divided by 3800, and I end up getting 0.95, negative 3800 divided by 4,000, and I also get 0.95, but this time negative. That means that R is negative, because to go from a positive to a negative, you'd multiply by a negative. To go from a negative to a positive, you have to multiply by another negative. So R is negative 0.95, but you can see that our values are still decreasing. So we'll go ahead, set it up in the sum formula. So I will have my first term, 4,000, times 1 minus negative 0.95 to the n, over 1 minus negative 0.95. And this should be in parentheses, that negative 0.95. From here, I will get 4,000 times 1 minus negative 0.95 to the nth, all divided by positive 1.95. So from here, if we're taking 95% of something, it's going to make it smaller and smaller. Same idea as this one. However, it's going to go back and forth between a large positive, large negative, smaller positive, smaller negative. And so what's happening to our terms is we're starting at 4,000, negative 3,800, and we're going back and forth, but each time getting smaller and smaller. So even though they're changing signs, they're still approaching 0. This is still, as n is going off to infinity, the negative 0.95 to the nth is going to 0. So if this is going to 0, we're going to replace it with a 0. So we'd end up with 1 over 1.95. And so then we could take 4,000 divided by 1.95, and we're going to get about 2,051.282. And so again, we would say that this converges, and this is the number in which it converges to. Unfortunately, WebAssign isn't going to accept this answer because this is a decimal, and so we can rewrite this fraction here with this decimal in the denominator is 1 over 195 over 100. From here, we'll flip and multiply the fraction, and so I will get 4,000 times 100 over 195, multiply straight across the top, and I will end up getting 400,000 divided by 195. You could type this into your calculator to make sure that it's equivalent, and it is. So this is the answer that you'll want to type into WebAssign, even though both of these are the same.